Hello. So in this video, we're going to talk about the definition of limits. Now, in the previous video, we kind of looked at the idea of a limit and how you're just kind of approaching that value. So the thing of which that we can establish is that the kind of like the notation, for instance, is that if I write down this expression, this means that I'm writing the limit as x approaches a for f of x equals to L. Now this is where it gets a little interesting. So we say if and only if that we write the limit as x approaches a from the left of f of x equals the limit as x approaches the right of a from the right of a for f of x. Now basically all that means is that the left limit has to equal the right limit in order for the limit to actually exist. How that actually looks in the x and y plane is very simple. We can actually just look at, just a random graph, for example, and we have that this could be x and this is going to be y. So let's say that, for example, that you have that there's a equation and you call it y equals f of x, and let's say that this is a, and then let's say that this is L. So we can kind of tell that if we follow along the graph with respect to the x-axis and we look at what's happening to the y values along the y-axis, we can see that we're approaching that from the left side, it's going to be L. That's that one. When we approach from the right, that's going to be also L, and that's that one. But what this does is it lets you know that because there's an agreement between um, between these two, like the left and the right, we should just say left. That way you don't get confused with L and. So since we have that there's an agreement upon the left and right limit, then we know that this limit does exist and that it equals to L. Because otherwise, if it doesn't match up, then we say that it doesn't exist. So let's try to look at an example though, because that's the best way that you're gonna kind of get these in terms of like finding, yeah, finding something like this. So let's say that we have the limit as x approaches 4 for x minus 4 divided by the square root of 4 minus not 4, sorry, um, that should be x, and then that's going to be minus 2. Now note that like if you do plug this in, that you are going to get 0 over 0, which means that this is an indeterminate form. But I want to say that, let's find this limit using a table. Now what we mean by that is that we're going to set up like a set of values. So like for example, we're going to set up a table like 1.9, 1.99, 1.999. Now at let's see, actually this should be 3.9. Yeah, so that should be 3.9. Okay, so this is going to be 3.9, 3.99, and then 3.99. Not sure why I was thinking 1, Okay, so 4, that's the one where it's undefined, technically, because if you plug in 4, you get 0 over 0. So we have 4.0001, and then we have 2 point, actually, I think that might be too many zeros. Yeah, yeah, so it should be just 4.01. And if you're kind of wondering, like, where do these values come from, it's kind of arbitrary in this sense, because we don't really know how close should we get to 4, which is going to come later, towards the end of the chapter. So we have 4.01, and then we have 4.1. Let's go ahead and just put it like right at the end. So we have 4.1. Okay, so basically we're just trying to plug these values into here. So you can think of this as kind of like your x, and this as your y. So all that we need to do is just plug in these values into this expression right here. Now, if we were to, let's say, for example, do where we have that we plug in 3.9 minus the 4, and we divide this by the square root of 3.9, and then we just plug this, not plug it, but subtract 2. So we subtract 2, and then we just hit enter. Well, we're going to get 3.9748. So that's going to be 3.9748. Okay, and we're going to repeat that process until we get all the values. So take like a moment to, plug these into your calculator and then see what you get. This one is the one that we don't know, so we can just leave it blank, or if you want to just put undefined, you can, because that's the way that the calculator is interpreting it, is that it's undefined, but we're going to figure out like what the limit value happens to be. Okay, so hopefully you've entered in these values into your calculator. Now, what you're basically entering into your calculator, just to clarify, is that you're plugging these values into this expression over here. If you want, you can actually plug this into your calculator, like y1 equals the square root of x minus 4 divided by the square root of x minus 2, and then just go to second, second trace, and then just select value. From there, just enter the x that you're looking for. But make sure that the window is big enough so that it can see like what's going on. So I went through the process of finding these. I mean, I could have shown you in the I could have shown it, but what I did was I went ahead and just started doing the rest of it like on the calculator on my end. So it's just a repeat. That's all I'm trying to say. Like, it's nothing glorious. So we have 3.9975. For 3.999, I got, so this is where you start to see like a pattern. So you get 3.9997, and then for the 4.01, you get, so this is where it's a little interesting, you get 4.00, I think it's 3 zeros, 2, and then this is where it gets like kind of like, okay, yeah, it's just getting like bigger. So we have 4.002, and then if we plug in 4.1, we get 4.02. Now, usually we try to do like 4 decimal places. I mean, you can go ahead and say like 2025 if you want, like for this one. And then for this one, that's 4 decimal places. And then for this one, I guess you would say 48. Now, the whole point of this is so that you can look at this and say, well, based on what we found, we know that the limit as x approaches 4 from the left side for f of x, we'll just call this expression f of x, equals to 4. But then we know that if we take the limit as x approaches 4 from the right side, so this is the right side, that's going to be also equal to 4. Now, based on this information, we can actually tell that, because the left has to equal the right, that the limit as x approaches 4 for f of x is equal to, well, that's just going to give us 4. So we have that the limit value is equal to 4. Now, knowing these table values, or I'm sorry, like these values, it all just depends on what you choose. Like whether you want to go 4 decimal places, then yeah, you can, or even 5 or 6. But I think like up to 3 or 4 is good enough. And then from there, you just kind of move outward. Now, I have that what I want to look at for this next example is let's say that we want to find the limit as x approaches 1 for x squared minus 1 divided by x minus 1. Now, for this one, what we can do here is just solve it perhaps like algebraically, because for instance, even if we do plug in 0, 1, you get 0 over 0, which doesn't really work for us. So what we can do here is just say that, okay, what's another way that we can do this? Well, another way that we can do this is that we can just rewrite it. So we have the limit as x approaches 1 of x minus 1 multiplied by x plus 1 divided by x minus 1. But what does this do for us? This tells us that we can actually just cancel out stuff. So we have that cancels out. Furthermore, it gives us the limit as x approaches 1 of x plus 1. But what is this going to equal? Well, based on this information about like how you just want to get close to the value on the left and the right, but even if you make like a chart like from the left or the right, you can tell that it's always gonna approach the same value. So in this case, you have that that's gonna equal to 2. So we have that that equals to 2. Now, I would recommend that you also look at, what does it look like based on the chart or based on the graph. So like if you were to draw the x plus 1, what you would see is that when you do x plus 1, this is approximately like what it's going to look like. However, you have that at 1, you have that there's a hole. So we have that there's a hole, and we can probably just do this a little better. So we have that there's a hole right there, and that hole is at 2. So it's the same thing really, like if you would have graphed this, that you would have said from the left it's 2, from the right it's 2, so that must mean that the limit is 2. So it's really whichever way that you want to. So I would say, try using a table if you want to use a table. Okay, so my next example, happens to be more or less the same with respect to how we can find a limit. So let's say that, for instance, that we look at how we can find the limit. So let's say that we want to find the limit as x approaches 3 for x plus 3 divided by x squared minus 9. Now, again, I look at this and I say, well, can I just plug in 3 and be done with it? But let's try it a little differently. So suppose that we go ahead and we say, well, I can tell that this can be factored. So I have that this is going to be x plus 3 divided by x plus 3 multiplied by x minus 3. But notice that basically you have that these two factors cancels out. So you have that that cancels out, that cancels out. So how does that reduce? It reduces as the limit as x approaches 3 for 1 divided by x minus 3. But notice this, that you have the, if you take 3 close enough to, or take x close enough to 3, basically you're going to find that this is going to be 1 divided by 0, which this is undefined, which essentially you come up with the same conclusion if you would have plugged in 3 into this equation expression. So then that would have gave you that this limit does not exist. Okay, so we have that the limit does not exist. Now, if we would have used the graph, basically, let's go ahead and look at if we were to plug this into um, if we were to plug this into our graphing calculator or even Desmos. So we have x plus 3, and this is divided by x squared minus 9, and then we just close it. So this is our graph. So we see that, and we can put like x equals 3 that way. You can kind of see what's happening. So this is our vertical line that's like an asymptote. So if I look at this, I can tell that from the left side that the equation is approaching, well, minus infinity. But if we also have over here approaches from the right side, we have it goes to minus infinity, plus infinity, sorry. So what this tells us is that the values are not in agreement. They're going to like infinity, and the other is going to minus infinity. So in this case, it does not exist because it's undefined. There is no limit. So if there is no limit, then yeah, we have that. We can't find it. So we can actually just draw this again. Like, you don't really have to, but like this just for clarification, that we have that there's a asymptote right here, and that you have that this will look something like that, and that'll be something like this. Now it is true that at -3 it's undefined, so you have a hole here somewhere, but I'm not going to bother looking for it because it's not related technically. So for here we have that the limit as x approaches 3 from the right of x plus 3 over x squared minus 9, that goes to positive infinity. Now be careful with the equal sign. I'm not saying that it equals infinity because infinity is not a real number, but I'm just saying that it tends to infinity. It's just notation, if anything. So if we look at 3 from the left side also, what you'll find is that that function goes to minus infinity. So they're both going to non-real numbers. So what that means is that basically that this limit does not exist. So essentially I get, obviously like the same thing, but at least it's a different way that, you can look at it. Normally, I would say you can also use the table values where you would use 2.9, 2.99, 2.999, and then you would use the next numbers, which would be like 3.001, 3.01, and then maybe like 3.1. The closer that you get to 3, basically you have that it'll go to minus infinity or plus infinity, which means that the limit does not exist. Now, in the event that I'm asking for the specific characteristics, like where does it go to, then you have to do it using the graph or the table values. But if it's just asking simply, what is the limit, then plugging it in would definitely give you also the same thing. But I wanted you to at least see that, sometimes you do have to factor and sometimes you don't. Now, what we can look at towards our end is that let's say that we have a limit of which we have that we want to find the limit as x approaches 0 for f of x, and this is going to be where f of x is defined as 1 for when x is greater than 0, and then it's a -1 for when x is less than 0. Now, this is where I'm basically forced to essentially just use the chart, or I'm sorry, use a graph. So we'll use the graph and we'll say, okay, well, if we draw our y-axis and then we draw our x-axis, all that we need to do really is just draw the graph. So at 1, so we have that for greater than 0, it's going to be 1. So we have that this is going to be 1. For less than 0, it's also going to be similarly, but -1. Okay, so this is -1 and this is 1. Now, this is one of those cases of where that we're looking at, how do we find the limit using the graph. So earlier we used the graph, but just kind of just followed along and just said what it was. So essentially, looking at this, I can tell that if I take the limit as x approaches 0 from the left side of f of x, this equals to -1. But I also have that the limit as x approaches 0 from the right side, if I follow this along here, so the right side, x greater than 0, I have that that's equal to 1. But they both don't match. They're both not equal to each other. So what that does is that implies that the limit as x approaches 0 uh, does not exist. Okay, so it does not exist. Now, another way that you can kind of tell when a limit does not exist based on a graph is whenever you have this big gap. So here there's what we call a jump. So whenever you have the jump or the gap, basically that means that the limit cannot exist because you have to have that they are in agreement to their values that they approach, but they don't. So in this case, you have that this does not exist. Okay, so my last example that I will give you is looking at, for instance, a piecewise function. So let's say that we want to find the limit as x approaches 0 for f of x where f of x is defined as the piecewise function. So we have that it's going to be 1 minus x squared for when x is less than 0. And then you have 1 minus x for when x is greater than or equal to 0. Now, I like this example because basically it's allowing me to kind of just figure out what the limit is. Now, let's go ahead and actually just draw the graph instead, because technically we're not supposed to be plugging it in, but it's okay because, that's exactly what you're doing. You're plugging in values that are to the left, right. Now, if I go ahead and I draw this in the x and y plane, well, if I draw this in the x and y plane, you're going to notice that basically it has like two different shapes. You have that it's parabolic from negative infinity to 0. So you have something like this. But then you also have that it's linear, but it's linear for when it's greater than 0. So the value, or the line, I'm sorry, the line looks something like this. Okay, so looking at this, this is 0, and this is the x-axis, and that's the y-axis. But here, right here is 1. So based on this information, I have that the limit as x approaches 0 from the right side. So the right side would be the denominator, 1 minus, not denominator, but the bottom rule. So 1 minus x, that would give us 0 based on the graph. But then I also have the limit as x approaches 0 from the left side of, let me write 1 minus x squared. That way it's a lot easier, or that way you can get an idea, like, where are we looking at. Oh, not 0, it's 1, right? Okay, so that's going to be 1, and that's also going to be 1. Now what this does is it implies that the limit as x approaches 0 for f of x, it's equal to 1 because of the fact that you have that at 0 for both sides. It's just going to be 1. So in that case, we have that, yeah, the limit value is just 1. Now, you can kind of see that basically you have several different methods that you can find limits. So, we know that basically that we can find limits by graphs. Those are the most easiest ones. The other way is by using tables. And then the other way is like thinking of it like numerically or algebraically. And then the other way is like the analytic method. The analytic method is when basically you're just rewriting the expression, like for instance factoring or multiplying by a conjugate. Like for instance, like whenever we looked at, say for example, the x minus 4 divided by the square root of x minus 2, you could have just multiplied by x plus 2 divided by root x plus 2, and then that would have gave you basically, yeah, it would have just gave you x plus 2, root x plus 2, because this would have became x minus 4 when you multiply it, and then that would have been multiplied by x minus 4, but they cancel out. So that's where I would have said that, okay, yeah, that just simplifies to, um, it just simplifies to root x plus 2, which is way easier, to be honest, because then you can just plug in the values that we were using, like 4. And notice that 4, root 4 is 2, 2 plus 2 is 4, done. So rewriting it is actually more or less beneficial. But if you would have graphed it, you would have found that if you would have graphed this one, that the graph of it kind of looks something like a square root, like something like this. But over here, you would have had a hole. But the goal is to, yeah, like figure out, not right there actually. Um, no, you would have had a hole at 4 actually. Yeah, that's right. So you would have had a hole at 4 because that's where it was undefined. I will just put like a small hole right there. Okay, so be sure that you kind of look through the different techniques of differentiation. I know that this was called the definition, and the next chapter, I believe, like you're looking at the techniques of not differentiation, techniques of finding limits. Um, but yeah, more or less, it's all the same. It's just using these specific methods and then just finding it. So it's more or less kind of intuitive when you're taking limits. But the main thing, though, is that you're comfortable with whichever method that you prefer. Okay?